This is EE698I, Mixed Signal IC Design, and this is lecture number 10. In the last class, we started to discuss how to implement a sampling switch, and we also started to see what are the non-idealities associated with the switch. The first thing was the finite on resistance, and if the switch has a finite on resistance, say R on, we saw that for a constant or a DC input of the form say V naught, the output was V naught minus the error signal V naught e power minus Ts by 2 R on times C, right? And as we discussed in the last class, even though your actual continuous time signal might be a time varying signal, so after sampling this, in most of the cases, we might want to process the sampled signal. So what we'll do is we'll sort of resample the signal by one more trap and hold or a sample and hold. Okay, so if I call this as my first stage, you can clearly see that the output of this first stage is some kind of a sampled and held waveform, right? So it will be something like this, right? And in this case, the input seen by this switch is a constant input of this form. Okay. And we saw that if the input was time varying and was of the form V naught cos of omega t, then the output had a transient portion like this, which decays to 0. And the steady state also had an error both in the amplitude and the phase, right? And the amplitude error was of the form V naught by square root of 1 plus omega square or on square c square. And we also had a phase error, that is minus tan inverse of omega or on times c, right? And for the first switch, which was the NMOS switch, what did we do? To turn the switch on, we need to connect the gate to VDD. Okay, so if this is my input, we saw that the on resistance of the switch was inversely proportional to the VGS minus VTH. This in turn is equal to VDD minus Vin minus VTH, right? So for a constant input that is close to 0, right? For constant input, if I say it's low, even on resistance is also low, right? This can be used as a good switch in that case. But if the input voltage Vin approaches VDD minus VTHN, what happens to the on resistance? The on resistance tends to infinity, and this is no longer a good switch. Okay. And please note that if the input is equal to VDD, and if we connect the gate to VDD, so what happens to the output voltage? Well, if the capacitor was initially charged to 0, the MOSFET will start to conduct. So this voltage will keep increasing, and the maximum it can reach is VDD minus VTHN, right? Because once it reaches this voltage, the gate to source voltage becomes just equal to the threshold voltage, and so the MOSFET turns off, right? And the on resistance becomes infinity. Okay. And this is with respect to the constant input. When we apply a time varying input of the form cos omega t, what happens from here? It's clear that the on resistance is a function of the input voltage. So the output will be of this form, right, which has a transient portion and a steady state portion. In the steady state portion, we clearly see that the on resistance appears in a nonlinear fashion. And so at the output, we will have nonlinearity. And similarly, we had the PMOS switch, which works as a good switch for a constant input voltage, which is close to VDD or a high voltage, right? And again, if the input is close to 0, the on resistance will tend to infinity. And if the input starts to vary, it will again have nonlinearity. And we also saw that we can combine both the NMOS and the PMOS switch and form what is known as the CMOS switch or the transmission gate. So it will look like this. So we take the PMOS and the NMOS and put them in parallel. So if we clock the NMOS by 5, the PMOS will be clocked by 5 bar, right? And this is a good switch and offers a low on resistance for constant input voltages all the way from 0 to VDD, right? So if it's a constant input, this is a very good switch. And even for time varying input signals, we saw that if we can ensure nu n Cox W by L of the NMOS to be equal to nu p Cox W by L of the PMOS, then to a first order, the on resistance becomes independent of the input, right? But we also observe that this condition is not easy to be ensured in practice, okay? And even if this can be ensured, please note that the equation that we assumed for the drain current of the MOSFETs is only a first order approximate equation, right? So in practice, the actual relation that relates the drain current to the gate and drain voltages will be more complicated. And so there will be, even if we can ensure this condition, the on resistance will still depend on the input. Okay. Not just that, for a MOSFET, we have 4 terminals, right? That is gate, source, drain, and bulk. We have only shown gate, source, and drain, right? So the bulk terminal or the substrate terminal for the PMOS can be connected to the source, which means for the PMOS, the source to bulk voltage will be 0. But for the NMOS, in most of the processes, we do not have any option and we have to connect it to ground, which means the source to bulk voltage of the NMOS is in turn equal to the input voltage, right? This is V in. This is also approximately V. Okay. As a result, the threshold voltage of the NMOS will be a nonlinear function of the input voltage. And hence, the on resistance will in turn show more dependence on the input voltage. Okay. So the bottom line is that the CMOS switch will still have nonlinearity for a time varying input, even if you ensure this condition. Okay. And please notice that this nonlinearity is an issue only when we are dealing with this kind of a time varying signal. If you are dealing with a constant input signal, that is a held signal like this, a CMOS gate works perfectly. Okay. So for successive stages like this, where we are sampling a held input which is constant, we can use a CMOS gate, a CMOS switch, and that will work perfectly in most cases. Okay. The problem comes when we are trying to sample a continuously varying input, such as this switch. So for this switch, we cannot use the CMOS switch in most cases because we might need very good nonlinearity or a very good linearity from the switch. And so we'll see how to implement this switch in this class. So if you look at the problem we have, the problem stems from the fact that for the NMOS switch, we try to turn the switch on by applying voltage VDD to the gate, right? And this is my input voltage. Okay. And we know that the on resistance is inversely proportional to VGS minus VTHN, right? And let's say this is approximately V in. So we know that the gate to source voltage is VDD minus V in. So if the input varies, when my gate to source voltage varies, and so the on resistance of the switch also varies. Now to make sure that there is no nonlinearity arising from the switch, all we have to make sure is that the on resistance is constant irrespective of the input voltage. To do that, what we have to do, we need to ensure that this VGS is a constant value. And what value can we make equal to? Well, we want the smallest on resistance and the highest voltage we have. So if we want to have a constant VGS equal to VDD, what do we have to do? Well, this voltage is input voltage, right? So that's going to vary. So to have a constant VGS of VDD, what do we have to do? We also need to vary the gate voltage by V, right? So to turn the switch on, instead of applying the voltage VDD, we need to apply the voltage VDD plus V, right? And how can we do? In principle, if this is V in, if I take an ideal voltage source of value VDD, okay, this will be what? VDD plus V, right? So this can be connected to the gate of the switch. This will ensure that we have a constant VDD or a constant gate to source voltage of VDD for the switch, and it will ensure that the on resistance is constant. But of course, we cannot have an ideal voltage source. So what we do, we use the next best thing we have, which is a capacitor charged to VDD. Okay, so let's say this is a capacitor that is charged to VDD. What we can do is the following. To turn the switch on, this is my input. We'll connect the other plate of the capacitor to the gate of the MOSFET. Okay, in that case, this gate will be VDD plus V. Okay, but of course, a capacitor is not an ideal voltage source, so it will start leaking its charge to the parasitic capacitors here. So after a few cycles, the voltage stored across the capacitor will start to reduce. So what do we have to do to counter that? Well, we need to keep recharging the capacitor to VDD. Okay, so what we can do is the following. When the switch needs to be on, say I call it phi equal to 1, and the switch needs to be on, we have the capacitor that is charged to VDD connected to the MOSFET like this. And when the switch is off, that is when phi equal to 0, what we have to do, we need to connect the gate of the MOSFET to 0. And in that phase, the capacitor is free, right? So what we can do is we can charge the capacitor to VDD in that phase. Okay. So now how will the complete circuit look like? So this is my main switch. Okay, I'll draw the sampling capacitor also here. So you need to have this capacitor. And in one phase, I want to connect the gate of the capacitor, gate of the switch to ground, right? And that happens when phi equal to 0. So what I'll do is the following. I'll have a switch here that connects the gate of the MOSFET to ground during phi bar. Similarly, in phi bar, we are also charging the capacitor to VDD. So I'll have one more set of switches here that connect the capacitor to VDD and ground. And this will be clocked by phi bar. In the other phase, I'm connecting the capacitor to the MOSFET. So you'll have something like this. So this is my V in. These are the switches clocked at 5. So in this way, when phi is 0, we are cooling the gate of the MOSFET to 0, so the switch is off. And in the same phase, we are charging the capacitor to VDD. And when the switch needs to be on, we are putting this capacitor across the MOSFET like this, so that we have a constant gate to source voltage. Okay, so this technique is called gate bootstrapping. And this switch is often referred to as the gate bootstrapped switch, or simply a bootstrapped switch. So now let's see how to implement these extra 5 switches, right? So let me just name these. So I'll call this M0. And let's say this is S1, S2, S3, S4, and S5. Okay. Let me just copy paste this. So first let's start with the switches S5 and S3. Okay. So if you look at these switches S3 and S5, what they are doing is that they are connecting this node to ground, and S3 connects this node to ground. So essentially the input to the switch is a constant input that is equal to 0, right? A low input voltage. So we can easily use an NMOS switch for this. So what I'll do, I'll replace the switch by an NMOS switch. And this needs to be clocked at 5 bar. I'll just call this as M5. Similarly, this switch S3 can also be implemented using an NMOS switch. Oops. It will be grounded, and this will also be clocked by 5 bar. And let's say I call it M3. So next, let's look at the other switches. So let me copy paste this. So now let's look at the switch S2. So the switch S2 here, what it is doing, it is trying to connect the top plate of this capacitor to the gate, right? And what will this voltage be? If this voltage is equal to V in, if I call this as Vx, Vx will be V in plus VDD when this switch is on, right? And if I call this as Vy, this switch S2 is trying to pass this voltage V in plus VDD from Vx to Vy, right? And since this is a high voltage, what we'll do, we'll try to use an NMOS, sorry, a PMOS switch like this. Okay, and this switch S2 was actually clocked by 5, right? Please remember. And since we are using a PMOS switch, we need to invert the clock and give 5 bar here. Okay, so this is the switch S2, right? So I'll call it M2. Sorry, this is my M2 switch. So what happens when we want to turn the switch on? We pull the gate of this transistor to 0 volts, and when it is on, this voltage is VDD plus V in. Okay, and the MOSFET easily turns on and make sure that this voltage is also close to this voltage. Okay, and when the switch is off, what happens? We pull the gate of M2 to VDD, right? And when this switch is off, the switch S1 pulls the top plate of the capacitor and connects it to VDD, right? So this is the top plate of the capacitor that's connected to VDD by the switch S1. Okay, and similarly, the other end of this switch S2 or this transistor M2, what it does, it's getting connected to ground by the switch M5. So I'll have this connected to this. Okay, And since this is connected to VDD, the switch easily turns off. There is no issues. Okay, so let me just label this M2. So let me copy paste this now. So next, let's look at how to implement this switch S4. So what is this switch doing? This S4 is trying to connect the voltage, input voltage V to this node, right? And if you clearly notice in the circuit, we also have one more switch that is doing a similar job, right? That is this switch M0. So that is also trying to pass this input voltage V, right? So what we can do, we can use the same kind of transistor for the switch S4 also. So we'll use a switch that is of an NMOS type. Okay. So this I'll call as M4. And this ideally needs to be clocked at 5, right? But to turn the switch on, if we try to apply a voltage VDD, that will not be enough, right? Because if the input is close to VDD, the switch will not turn on. So we had a similar issue with this transistor. And what did we do? We are trying to connect the gate of the transistor M0 to Vin plus VDD, right? So we can do something similar for this transistor M4 also. Okay, so what we have to do is the following. When we want to turn the switch M4 on, we wish to tie the gate of M4 to Vin plus VDD. And when we want to turn it off, we want to connect it to 0. Okay, this is ground, right? But if you clearly notice, when phi equal to 0, that is when phi bar is 1, what happens? We want M4 to be off, right? So we want the gate of M4 to be 0. And we notice that when phi is 0, that is when phi bar is high, this transistor M5 is pulling the gate of the main switch M0 to be 0, right? So this is also equal to the gate voltage of the transistor M0. And similarly, when phi equal to 1, we ideally want the gate of the transistor M4 to be Vin plus VDD. And when phi equal to 1, we clearly see that this transistor is on. So what will happen? This voltage, that is the gate of the transistor M0, will be pulled to Vin plus VDD, right? So what can be done is the following. We can connect the gate of this transistor M4 to the gate of this switch M0 itself. Okay. So what happens now? When phi is 0, that is when phi bar is 1, this transistor M5 connects gate of both M0 and M4 to 0. So both of them will be off. And this capacitor is charged to VDD, right? And when phi equal to 1, that is when we try to turn the main switch on, what happens? These two switches are out of the picture. And this switch is again turned off. Okay. And initially this switch is on, right? So this M2 will be on and it will connect this terminal of the plate to this voltage. And please note that initially in the previous phase, if I call this voltage to be Vx, Vx was charged to VDD, right? At the end of the previous phase when phi equal to 0. Okay. So just when the switch turns on, if I call the gate voltage as Vy, Vy will also be equal to VDD. Okay. And this will start to turn the switch M4 on slowly. So which means this voltage will start getting charged to Vin slowly. That is Vx will start to increase. which means Vy will also start to increase, which will in turn turn the switch M4 on further and further, and eventually M4 will completely conduct and connect this node to V. So this will become V in, so which means the gate voltage Vy will become V in plus VDD, and the switch M0 will also turn on with a constant VGS of VDD. Okay, so now we are left with only this switch S1. So let's see how to implement that. So S1, how do you implement it? Well, we see that this switch S1 is trying to connect or trying to pass a voltage VDD, right? And since it is a high voltage, we can use as PMOS switch, right? So this will be a PMOS switch. Okay. So to turn this switch on, what do we have to do? We need to connect the gate voltage to 0, right? And the switch will turn on. And let us say we want to turn the switch off. If I call the transistor M1. So to turn M1 off, we need to connect the gate voltage to, if we try to connect the gate voltage to VDD, so what will happen is the following. This is M1, this is VDD, right? And this left side is VDD. So when this switch is off, what happens? This switch is on, okay? And this switch is also on. So the top plate of the capacitor, that is the voltage Vx, will be connected to V in plus VDD, right? So this will be at this voltage V in plus VDD. And we know this can go as high as 2 VDD, right? Because V in can reach as close to VDD as possible. So which means what will happen for an NMOS, for a PMOS, the terminal with the highest voltage will act as the source. So in this case, this has the highest voltage. So this will become the source now. Okay, so let me turn the arrow this way. So this will become the source now, right? And we can see that the source to gate voltage is equal to VDD. And so this transistor will start conducting. Okay, so when we try to turn the switch off by applying a voltage VDD, it doesn't turn off, but instead it starts to turn on. Okay, so that's a problem, right? So what do we have to do? We need to make sure that the switch completely turns off. And one way to do is to ensure that the source to gate voltage is 0, right? And that can be done by connecting this gate to voltage VDD plus V, right? And that will ensure that the source to gate voltage is 0 and the switch turns off. And please note that in the circuit, we already have one node that is equal to V in plus VDD, right? That is this node, that is the gate of the transistor M0. And also notice that when the transistor M0 is off, what happens? The gate of M0 is pulled to 0 volts by switch, this switch, okay? And this happens during phi equal to 0, right? And during phi equal to 0, what do we want? We want the capacitor to be charged to VDD. So which means we want this switch to be on, right? And to turn the switch M1 on, we also need the gate voltage of the transistor to be 0 volt. Okay. And similarly, when phi equal to 1, when we want M0 to be on, we want the gate voltage of M0 to be P in plus VDD, right? And when this transistor M0 is on, that is when phi equal to 1, we want these two transistors to be off, right? So which means we want M1 to be off. And we saw that to turn M1 off, the gate voltage must be P in plus VDD, right? This is in turn equal to the required gate voltage for the transistor M1. So what do we have to do? I mean, what can be done now? We can simply take the gate voltage of M1 and connect it to the gate of M0 like this. So this way, the gate of M1 will be connected to the required voltage to turn it on or off. Right? So the final schematic is going to look something like this. So this is the main switch and the sampling capacitor. This is M0. So gate of this switch, oops, the gate of this switch is pulled to 0 when phi is low, and we have a capacitor here whose bottom plate is connected to ground when again phi is low, right? And the top plate needs to be connected to VDD, and this switch is connected to the gate of the main switch. And we have the other switch here, clocked by phi bar. And we have one more switch here, which is an NMOS switch, okay, whose gate voltage is also shared with the gate of the main transistor M0. Right? And these are my transistors M1, M2, M3, M4, and M5. Okay. So this is the overall schematic of the gate bootstrapped switch. And this switch will operate, that is this switch M0 will operate with a constant VGS of VDD. And so the on resistance is going to be constant irrespective of the input voltage we have here. Okay. And as a result, when it processes time varying inputs, this switch will exhibit excellent linearity. And this is the schematic, I mean, this is the bootstrap switch that is used very commonly recently. Okay, so in most of the designs which require a high linearity, this is the switch that is used. Okay. So there is another variant which was used earlier. So let me just explain that also for the sake of completeness. So first let me copy paste this. Let me say variant 2. Recognizing the fact that the gate voltages of these transistors M1 and M4 can actually be shared with the gate voltage of M0, what was done was the following. So let me just delete these things. So this switch is clocked by phi, right? And notice that this switch is trying to connect Vin to this node. Okay. So which means since Vin can vary all the way from 0 to VDD, it is going to see a wide range of input signal, right? And the best switch we know that can pass a wide range of input signal is the transmission gate. So here a transmission gate was used. Okay. So this needs to be clocked at phi. So the NMOS is clocked at phi and the PMOS is clocked by phi bar. Okay. And for this transistor M1, we saw that to turn this on, we can apply a voltage of 0 volt, right? But to turn it off, it was not enough if we connect the gate to VDD, right? So we saw that if we try to connect VDD here, it was not enough to turn the transistor off. And so what we need to connect this voltage, connect this gate to a voltage VDD plus Vin, right? And since Vin can go all the way to VDD, this voltage has to be equal to 2 VDD to make sure that this transistor definitely doesn't turn on. Okay. So ideally, if you're not connecting this to the gate voltage, we would want to ensure that this switch is always off irrespective of the input voltage. So we would want to connect the gate to VDD to turn the switch off. right? So this would require that we need to generate a clock going all the way from 0 to 2 VDD, right? And this will require higher voltage supply as well, right? So instead, people started to see what happens when we use an NMOS switch. So let's say I use an NMOS switch. Okay. So obviously, since it is trying to pass a voltage VDD, to turn the switch on, it is not enough if we connect this gate to VDD, right? So we need to connect this to 2 VDD to turn this on. But please note that to turn the switch off, so let me draw the switch separately here. I'll call this M1. This is VDD. When this switch is off, this voltage is connected here, right? This M2 is on. We have this path on, right? So which means this voltage, which is this, will be Vin plus VDD. And we know this can go as high as 2 VDD. Okay. So to turn this switch M1 off, we do not have to connect the gate to 0 volt, right? So we can simply connect it to VDD, because connecting it to VDD will make sure that the gate to source voltage is 0, right? And the switch turns off. Okay. So if we want to use an NMOS switch, the gate voltage has to swing from VDD to 2 VDD, right? So this means that instead of having a clock going from 0 to VDD, we now need a clock that is shifted up, right? So it has to go from VDD to 2 VDD. So let me draw it like this. It has to go like this, right? So if this is 0, this is VDD, this is 2 VDD, right? And this is much simpler to achieve. And how do we do that? Well, we use the same old trick. So let us say we have this clock 5 going from 0 to VDD. What we want, we need to generate a clock 5 plus VDD, right? So how do we do that? In principle, we can use a voltage source of value VDD, right? That will guarantee that the output will be a clock which is 5 plus VDD. But of course, we cannot have an ideal voltage source. So what we do the same old trick. We use a capacitor that is charged to VDD. Okay. So this capacitor has to be charged to VDD. And when can we charge it? Well, when phi is 0, we want the output to be VDD, right? So when phi is 0, we can simply charge this capacitor to VDD, right? So this has to be clocked by phi bar, right? Only then when phi is 0, the switch will turn on and this will be equal to VDD, right? And when the switch turns off, phi will be equal to VDD. And since the capacitor was charged to VDD in the earlier phase, the output will become 2 VDD, right? So now how do we implement the switch? So let's see how to do that. So let's say I use an NMOS switch here. So I have the NMOS switch here, right? If I try to connect this gate to phi bar, that goes from VDD to 0. What will happen? Well, to turn the switch on, VDD is not enough, right? So this voltage has to be 2 VDD to turn the switch on, right? But also note that to turn the switch off, we don't have to connect the gate voltage to 0. We can simply connect it to VDD, right? So instead of having a signal phi bar, what we need is the following. We need the gate to be connected to phi bar plus VDD, right? So this is my required gate voltage here, right? Which is phi bar plus VDD. And how can we generate that? Well, we have a signal phi. I'll give it to an inverter that will generate the signal phi bar. So if phi goes from 0 to VDD, this will go from VDD to 0, right? And again, if I have a capacitor that is charged to VDD, this will give me phi bar plus VDD, right? And obviously, this capacitor has to be charged again. So I'll need to use one more switch here. So if I use the same NMOS switch, this gate voltage what should it be connected to? It needs to be connected to 5 plus VDD. Right? You can simply guess from this portion. Right? Now you notice that this gate needs a voltage 5 bar plus VDD, and we have 5 bar plus VDD available here. Right? And similarly, this gate requires a voltage 5 plus VDD, and we have 5 plus VDD available here. So we can simply connect the gate here and this gate here. Okay. So this will generate the clock 5 plus VDD and 5 bar plus VDD, which will swing from VDD to 2 VDD. Okay. So let me draw it more cleanly. So this is connected here and this is connected here. Okay, and this circuit is called Nakakomi charge pump. Okay. And this was often used, okay, along with this circuit to generate this clock. Okay, and please note that this CM1 needs to be clocked with 5 bar, so this had to be 5 bar plus VDD. Okay, so we can use this charge pump circuit to generate the required 5 bar plus VDD and connect it. And this was what was used earlier. But after recognizing that these gate voltages can be shared with the gate voltage of this main switch, people have started to use this circuit, which is much more elegant and clean. Okay. So we'll stop at this point and continue from the next class.